So I haven't I haven't put the homework up yet. It's kind of taken longer to read through it. I might make it, so that's like dead. I haven't written it yet. But it's on this paper. I'm kind of reading through this paper. It's taken a little bit of time to do it, I guess. Um, anyway, so it might be that maybe we'll delay the homework or something this week because I didn't put it up. Usually I try to put it up Monday and it's already Wednesday, so it's kind of like a couple of days behind. See how it goes. I'll have it done by Friday, but anyway, so the papers on this thing's about this kind of blob idea. So these are bottle brush polymers. So they can be comb polymers or bottle brush. They're kind of the same thing. Like you have a chain in the middle and you have chains on the side. It's like a kind of, I guess the original of this would be like linear low density polyethylene is kind of something like this, except the chains on the side are only like 8 units long or 6 to 8 units long. So they aren't exactly full chains. These are like polymer chains and then a backbone polymer chain. So anyway, so kind of that's been looked at pretty extensively and they have some ideas about how like properties you can get from these things. So I'll talk about that on Friday, but it has this idea of blobs in it, which is a topic. So anyway, um, so the blobs, there's kind of basically what four kinds of blobs, like three kinds, and then you can call a Kuhn unit a blob also, and then maybe five if you call it collapsed coil, and if you include like the electrostatic um, polyelectrolytes, then there's a electrostatic blob also. I should probably put that on this table. It's actually six, seven, I guess. Six. It's probably more. Like you could probably make more. So I can go through the kind of the concept of this, but the simplest one is the tensile blob, and it's also called the tension blob. So there's different names, different people call it different things. So we had like the chain, we had this business to get the modulus of a chain. It was going to be like 3 kT over NL squared, so the modulus. So the higher the molecular weight, the weaker the kind of rubber, say. Like if you make a rubber, you cross-link the ends of these chains, that's going to be the modulus of the rubber, right? And the higher the molecular weight between crosslinks, the looser the rubber, the lower the molecular weight between crosslinks, the stiffer the rubber. And then as you raise the temperature, the rubber gets softer. No, when you raise the temperature, the rubber gets stiffer because the chains between crosslinks are kind of like a jump rope. So the faster you spin them, it pulls in tighter. So it's the opposite of softening when you heat. It kind of stiffens when you heat. And it softens when you cool it down. So anyway, so that's the standard thing that existed in the 1950s, I guess. There's a book by a guy named Trelor, Trelor, which is on the webpage that goes through rubber elasticity. I think it's published in the early 60s. I think he's a British guy, as far as I know. But so anyway, so this whole model is based on the idea of like small perturbation. So you just barely stretch the chain. But say you're in a case like this. Let's see, go back like this case where you have, so there's a lot of perturbations to the chains when you start making this kind of millipede polymer, right? So the side chains get stretched out and the main chain gets stretched out, and it's not a small perturbation, especially if you can get this many side chains onto it chemically somehow. Right? So anyway, when you get to large perturbations, then things get a little kind of interesting, I guess. But so also, like if you graft polymers onto a surface, like you want to make this would be if you wanted to make like a biocompatible surface, or if you wanted to say the polymer had groups that could attach to like a biocide molecule, then you could make a biocidal surface. It's kind of like permanently biocidal because say you could put gold or silver atoms into it. then it would be like a permanently biocidal, like it wouldn't wash off because these things are stuck to the surface, bonded. So that exists, you know. So you want to know a little bit about like what's the thickness of that layer, um, as a function of the molecular weight that you put into it. Or so you want to have kind of synthetic control over what you make. So people have looked at that. So this is a kind of an example of a tensile or tension blob, that idea of a surface grafting. In the simplest case, you can kind of do you can do, if this guy's running, so you can just kind of model what's going on with the chains. Let me grow these, so I put it in a bag. This is going to work, kind of. All right, so zoom out. So you have something like, say this cable. This is what I could find in my office. So you could do this with a string too. So that's a random walk site. And then you start to pull it. So theoretically, in the internal part of this is moving by KT. So each of the monomers is shaking like a jump rope. So they aren't static like this. So they kind of the springiness of this thing is proportional to KT. The higher the KT, the more springy it is. Right. So basically you pull on it, and then and I said also that the modulus is 3 KT over NL squared, so it's one over the molecular weight. So for the whole chain, there's not much modulus, right? But if I look at a small part of it, the modulus is pretty high, right? So there's a dependence on the molecular weight of the modulus of things. It means it's going to give at the largest sizes, and you kind of see it in this like it starts to form this thing that's like linear, right? It starts to form a linear structure. If I pull it more, finally, it's going to form a thing that's L, like the number of Kuhn units, and the Kuhn unit, the final length would be like that. The initial length would be, the initial size is going to be square root of NK times LK. Right, so there's a pretty extensive change, like the how much you could stretch it is like that much. But as it goes through the stretching, it's not a uniform stretching. Like in a local scale, it still follows that. And on a large scale, it follows that immediately. Like immediately when I first pull it, it forms a thick rod. And as I pull it more, it forms a thinner rod, right? Because I'm probing, because the force is balancing against this 3 KT. Right? In other words, force times some distance gives you energy. So force times some distance gives me the 3 KT that I had for the modular, 3 KT over NL squared. Right? So the energy parts the 3 KT, that's got to balance against the force times some distance. Force times distance is energy, right? So you need some distance. So you call that distance a tension blob or a tensile blob, depending on if you want to use an adjective or a modified blob or kind of a noun to modify it, I guess. So I think tensile is the right one, but anyway, in this paper for tomorrow, he's using tension, he calls it, but it's the same thing. Right, so that's the idea. So that's basically because you have a structure that has a lot of different molecular weights in it, and then when you perturb it by pulling on it, or some other kind of perturbation, then you get a size scale is invented by the thing. The combination of your perturbation and the structure generates a size scale. So there's no other material that does that. Only polymers, and only kind of linear polymers pretty much do that. All right, so that's a unique feature of polymers. I mean, for whatever it's worth, it means you have to kind of look at the thing in a different way, right? So you got to say, you know, how does this work? Well, this is molecular weight dependence to the properties, and the molecular weight on a small scale is different than on a large scale. So I'm going to get this introduction of a new size scale that's a transition point between rod and random walk, or a good solvent, depending on what the solvent is for the thing. So that's called a blob. Anyway, that's size scale. So if you wanted to take a picture of the thing, like I can show you the thing, and you can say like, well, here's the thing, you know, what's the blob size? So you can't exactly pick it out. You know, like I could do it different ways, and so it's not exactly a thing you can see in a micrograph. but it's definitely a thing you can see in scattering. Because scattering doesn't look at things like individual things, it's going to average over the entire system. So billions of these things. And over billions of them, it actually has a size scale you can measure. Right. So if you want to look at this, so it's kind of better to look at the whole thing in terms of just scattering and forget about the cartoon of what it is. Even though the whole thing, the math of it's going to be based on the cartoon of what it is, which can be misleading. So in terms of scattering, like you're looking for scaling, you have log I, log Q, and so at large scales, so first off, you have the chain, and say it was Gaussian, so you have -2, and then you have the persistence length, -1, right? So it's like 2 pi over LP, and Q star. And then as you pull it, I should have made more over here, but as you pull it, it's going to get larger. So this is the coil size R, or 2 pi over R, and that R is going to get larger, so this gets smaller. This kind of Q double star. And then, so what's going to happen, it's going to go to a shallower slope, and then it's going to come down, and then you know that this transition size is getting smaller. So this blob size is getting smaller. So the transition point between two, and that transition size starts out as a size of R, and then it's going to get smaller. So it's going to be R times something of the force. That's going to be, so in fact, it's kind of 1 over force. It's going to give this blob size, right? So basically, you can start writing math about this. In terms of the plot here, this is going to take off at the -1, so it's going to be a shallower slope. It's going to come over like this, and then the transition, so this is -1, and then the size gets larger, until finally, at the maximum extension, let's see, I did this wrong. This number here, the intercept, is the number of units in the system times the electron density squared of the thing. So that's a fixed number, like the number of Murray units times electron density squared of the Murray units. So that number is fixed. Let me do this plot again. Sorry. Log Q, log I. So you have a fixed number, this n rho squared times d squared. That's fixed. It's the same molecule you're doing. Then you have the -1 out here, and then you have the persistence length, right? And then you have the -2. Think about you have the -2 part, and that's your original R. And then if you're going to make it get longer, so this introduces a -1 here, and that becomes a blob size, the tensile blob size, and your new R here is there. That's R under some force F, and this guy's a function of F. Right, so the more you pull it, this will go down, and this guy moves over. So finally, it's totally stretched, and it will be like here, and that would be L. That's the contour length. That's the Murray unit, Kuhn unit times the number of Kuhn units, the total possible length it could have. Right, so it's a little complicated, but it's not that bad. So this is as you stretch it, so this way is forcing, and that way is force, putting more and more force on it. You can finally fully stretch it out like that, and that's the length of the cable. That's as far as you can stretch it, and it's stuck. And in the material, the composition of the material, this number is fixed throughout, because you have the same polymer in there. So the composition of the polymer is just stuck with that number. So the intensity of that zero intercept's got to be fixed. And then all the actions, like within the thing, your R is going that way, and your blob size is going that way, because blob size is getting smaller. So 1 over blob size gets larger, and the coil size gets larger. So 1 over coil size gets smaller. It's kind of the action that's going on. Right, so that's easier. If you draw the cartoon, you have that thing, and it goes to kind of that thing, and it goes to that thing, and finally it goes to that thing. Going like that, right? So your blob size is kind of that thing, and then this thing, and then something smaller, and then finally it's just like it's 1 or whatever, 1 Murray unit diameter. Right, so you can see that's kind of useful to describe like the scaling behavior of the chain. It isn't exactly analytic, like what you get out of this, because all this is a little bit the equal sign is really a squiggly thing, like it's just a proportionality, right? So you don't know exactly what the size is, but you know the dependence on the force here, which is kind of the important thing, right? So anyway, so that's kind of how the tensile blob thing. So let's see. This isn't the newest version of this thing. Oh, why is that? That's pretty weird. Let me get the newest. I should have the newest version. Uh, I downloaded it. I uploaded it and downloaded it. This happens sometimes. Not sure why it does it though. Well, this thing is slides 3 here. See if the PDF has a newer version. Yeah, this is the new version. It's got red things in it. And why doesn't the other guy have it? Where is this again? Slides 3, PowerPoint. That should be that. Did it open? Let's see. So go here. Maybe it didn't open because it's already opened. No. Does this have red stuff? No. All right, so somehow I didn't download the other one. Anyway, it doesn't matter that much. Anyway, so this looks a lot like let's see. This is what I want. I want to go back this, this, this. All right, so it looks something like this idea of Vigerum length and the Debye screen length. So here when you're at sizes larger than the this is actually different, right? Let me just go back to it's different than this thing. Why? Go from this. Just go off this thing. So let's see if that'll work. That doesn't exactly work too good. All right. Yeah, this is different than that of the slide, right? So anyway, that's kind of weird. Like it's totally different. I think it didn't get any of the modifications of this. It's weird. Wait, so this for Vigerum length, if you go larger than that, you have mean field behavior. And if you're smaller than that, if it's a polyelectrolyte, you get rod behavior. So in this case, it's like a persistence, like you're adding to the persistence length of this Vigerum length. So you start with persistence length, and then you add on because the charges repel each other. It makes the thing go straight. That's the opposite of what's going on with the external force thing. So you can say, the reason I mention that is you can talk about like external perturbations or internal perturbations. And internal perturbations start from the small size and work their way out. So internal will be like charging the chain. So you're driving the chain to be straight by putting charges on it locally, right? Versus externally, you pull on the chain, which makes it straight at the large scale and random at the small scale. So that for everything that you can do, there's kind of a parallel thing you could do, like an alternate universe. Listen to this science fiction Netflix thing. It's like the alternate universe. You have the universe of external force on it that makes it linear, then random at small scale. You can do an internal and it makes it linear at small scale, which is similar to persistence, which is like the chemical makeup of the chain. Like that's internal. So persistence is linear at small scale, and then you get random at large scale, right? So there's a flip between them, and that's true of all of the blobs. They all have partners that are the other way around. So it's kind of an odd thing, it seems like, but basically all of them have an opposite partner like that. So here you could say the Vigerum length, the Debye screen length makes a chain linear at small scales and then random at large scales. And an external force, a tensile blob, makes it linear at large scales and random at small scales. both introduce a size scale. So no matter what you do to the chain, you're going to be introducing a size scale to it. So you create a new size scale by doing some perturbation to it. That's the idea, right? So anyway, so that said, so we've already gone through those other two, so let's mention it here. And then these are the ones like thermal, thermic, concentration, just as the one name. And then tensile is the one I just went through. It's also tension. And these are the people that kind of found those out. So you'd think that the tensile blob would be the first one that was discovered because it's the simplest one. And it's kind of obvious when you put like a cable on the table that happens, right? And the others are more involved. But actually, the first one, I think the first one that was done was a thermal blob, which is the most complicated. And then the concentration blob afterwards, or maybe around the same time. And then this tensile blob, not until the 1980s or something like that. So a lot later. So these were like, thermal was something like in the 60s, late 60s, early 70s. And then concentration is like mid 70s. And this is like 80s, 90s. So it's kind of like the simplest one is the last one that was found out or like talked about. So, and then even into the 2000s is this kind of collapsed coil thing that when I talked about collapsed coil, I said like a small scale, it goes to three-dimensional balls, and then those form like a Gaussian walk at larger scale, right? So the collapsed coil is another kind of blob, and he even calls it I think he calls it a collapsed coil blob or something like that, for the Russian guy that did that. So anyway, so you can keep adding on. Like I said, there's an electrostatic blob too that Colby talks about at Penn State, right? So people are adding on more blobs as time goes by, I guess. But so this is kind of the picture of it. So then these other two that are like the major ones is a concentration blob. So the idea is like, so you have the chains that are in dilute solution, so they're individual chains or clusters here. And then so any kind of colloid will do this, so it's like dust particles will do this too, or like silica filler or carbon black filler that are these kind of open fractal structures. They're all going to have an overlap concentration, or even like nanotubes. So rod structures have an overlap concentration where they start to interact, right? So once you get to the overlap concentration, then you can't see the structure anymore. You can't see the individual polymer, right? So then the system, so you've introduced a size scale. I mean, in scattering, it's kind of obvious because so in fact, I think this was first talked about from scattering perspective. So if you have the system log I, log Q, then you have it in dilute solution. So it's going to go -5/3 good solvent, and it's going to go -1. Then if you go, that's below C star. If you go above C star, well, above C star is just a uniform system. We can't see any structure. So its size scales above this kind of blob size. You don't see anything, and then all you see is basically this blob size, this concentration blob. And as the concentration goes up, you see less and less of things. So this is concentration going up. And in the structure, you have an individual coil for that one. And then for this one, the coils suddenly overlap with each other. So you can't see, if you took a micrograph, you couldn't see an individual coil. You just see that mess. But if you zoom in, right, you still see the same thing. So either one of them zoomed in shows the same thing. So if you see at a small scale, you see this, and then at some point you see just nothing. You can't see any structure. That's the transition point. That's this concentration blob point for the thing. Okay, so there's some point where you see that. So people want to know, like, how does that thing depend on concentration? And then how does the coil size depend on concentration? Those are kind of the two key things, because the thing you're varying is concentration. So in fact, what happens is once you go above the size scales above this overlap, this concentration blob size, then the coils are actually Gaussian. So that R goes with n to the 1/2 L. You have Gaussian scaling there, and then you have the good solvent scaling here at the small scale. Right? And then you have this transition size. So to measure that, so you would go in and get use neutron scattering, and then tag one of the chains with pull the things out of there. Maybe they're all the tricks. I don't see it. All right. So anyway, you tag one of the chains with a different color. You just, I don't have a different color, but one of the chains would be like deuterated, so it'd light up. And they just have a mess of the other chains. And then you could see that this thing, where you have this blob, you would see the transition. Where you have the -1, and then this is 5/3, and then it would go to 2. And draw it right, but be like that, and then 2. Right, and then you get the coil size. So that would be the coil size. So in that case, if you looked at one chain that was lit up with deuterium, you'd see a transition to Gaussian here. So you'd have, in that case, if you plotted it out as a function of concentration, log Q, log I. See, this number is fixed because it's the same chain. That's your n rho squared v squared, and then your persistence length is fixed. That's kind of fixed. And then in the case where it's a good solvent, you have this weaker slope, kind of like that. It goes up to here, and it go one shallower. And then that's your R when it's in a good solvent, and C is less than C star, overlap concentration. And then you're going to introduce this, so then the coil gets smaller. So it's going to go like that. And as you increase the concentration more and more, that blob size gets smaller, and the coil gets smaller also. Right. So this is kind of where you stop seeing. That's the size scale where you stop seeing. Like if you have a fleece and you can zoom in, at some point you can see a fiber. So that point where you can see a fiber, that's this transition size. And above that, you see nothing unless I put a red fiber in here, and then you could see the red fiber. You could see that it had that scaling transition. All right, so that's been verified by experiment. So that's kind of like easy to verify with neutron scattering. Can't do it with X-rays, but basically you can do it with neutron. So anyways, that's the idea of the way the concentration blob works. So the thermal blob. So the idea with the thermal blob is that the interaction for the large chains, so the collapse is the opposite for the thermal blob. You get local collapse, and then you get good solvent scaling at the large scale. So that I'll talk about it after this, because that's more complicated to deal with. All right, so that's the tensile blob stuff. So tensile blob is what the paper's about this week. So that's kind of a simple one. So concentration blob, I mean, the first thing people did was they figured out that it's going to depend on C star. So that, and you get the molecular, so you want to know kind of like the molecular weight dependence of the chain under different concentrations. So you have C star depends on the molecular weight because it's going to be the mass of the chain divided by the volume. And the volume is 3/5 cubed, which is 9/5. You end up with -4/5 for the C star. That's the kind of the density of one chain. What you have one chain of mass n, and what's the density of it? It's just n to the -4/5. So above, once you get above the overlap concentration, you can't see a single chain, so n has nothing to do with anything. So C star is defined by n, but the chain, nothing of the structure is affected by n above C star because you can't see the ends of the chains anymore. It's like if I show you this fleece and I say, what's the molecular weight of one fiber in the fleece? What's the length of one fiber? You can't say. right? So you have no information about n once you're above C star. That's key to this whole thing, right? So then you can say, see, that's the thermal blob stuff. What's this thing? Sorry. So then you can say, so you have this -4/5 for C star, and you can say there's no dependence above C star on n. So what's the value of this thing? So you can say, well, that thing, if you're at C star, that thing has to be the coil size R. And then above C star, it's going to depend on the concentration normalized by C star, because that's the parameter of interest. So you say, well, you're going to say it's a scaling dependence because everything's a scaling dependence. So you say it's P. You know that R is 3/5 because it's a good solvent chain. So you have n to the 3/5 for the R part. Then C doesn't depend on molecular weight, and C star depends on -4/5. You can say 4 times P, and then 3 plus 4 times P by 5 gives you the dependence of that thing on n, but this thing can't depend on n. Or let's see, there's no dependence on n, so you can get what P is here. And P is the power of the concentration, right? So you say this thing has to be 0, has to have no dependence, then you can solve for P and find out it's 3/4, -3/4. You can say that the blob size depends on -3/4 of the concentration. So you can plot this blob size, we can measure with neutron scattering, or with X-ray scattering, either one. That's basically just the tailover part of the curve. So as the curve diminishes with concentration, then you can, the tailover part that looks like RG is the size, you can just measure it with X-rays or light, right? So that would be like the rate of gyration that you get as you increase the concentration. That's going to depend on concentration -3/4. So that's easy to verify. I think that's been verified. And then you can say like the coil size. Once you have that number, then you can say, well, what is R? It's going to be that number, and it's Gaussian above that. So it's going to be a Gaussian walk of blobs. So you need to know like how many of these concentration blobs are there. To the 1/2 gives you the R. And the concentration blob size you can get from this, because this thing's going to be a good solvent at the small scale. So the total molecular weight divided by the molecular weight of one of the blobs times the Kuhn length would give you this thing. So, and you know, that thing depends on C by C star to the -3/4. So you can solve for this, how many are in a blob in terms of C. It would be like C to the C to the 3/4 is 1/, and then to the 5/3 from this thing. So you get that thing in at 5/4 for how many are in a blob. If you know how many in the blob, you know this thing is to the -3/4, and that thing's going to be 5/4, 1/2 gives 5/8. Then you end up with that the size of the coil has a weak dependence on concentration to the -1/8 power. So the higher the concentration, it gets smaller. This thing has a much stronger dependence on concentration. Right, so you can get the whole picture of how the structure changes with concentration from that. And that's verified by neutron scattering. Right? So it's a nice picture. It's like a nice knitted picture of how your perturbation in this case is just increasing the concentration. Then you get these scaling of these two things, and they matches up with experiment. Right, so you can kind of understand how the system's put together. Right, so anyway, so that's that business. So that's our concentration. So at large scales, it's Gaussian. At small scales, it's expanded coil. And as you increase concentration, you lose this and gain that. Right. So the tensile, and then we know about the Kuhn, which is the opposite of tensile. So Gaussian large, linear at small. And then this thermal's the last guy here. So and people use this model. This is like the Dowd-Cotton model for polymers grafted to a sphere, say, or maybe a dendrimer or other things. Like you're going to have like a transition in concentration. So it's using the concentration blob idea, but it's saying like if you have a radial distribution, so you have chains tethered to the surface and then attached to a sphere, so the concentration changes as you go out. So you get a change in the concentration blob size as you go out, and you can talk about the corona around a sphere with grafted polymers stuck to it. which is a thing. It's one way to disperse colloids, like because of the repulsion between the polymer chains at the surface that makes them suspend in a solution. Anyway, the Dowd-Cotton model is kind of a big thing, I guess people use for looking at colloids. Anyway, so we did, all right, so the thermal blob or thermic blob, depending on how you want to use the prefactor, describes like this behavior that we saw before. So we already have like, we got the Flory-Krigbaum equation. So chi is 1 over T. So this describes the temperature dependence of the size of the coil overall, right? But the idea is that so at the theta temperature, the chain is entirely Gaussian, right? And then the minute that you step away from that, it should be entirely random walk, because it's a self-avoiding walk once you get to have an interaction parameter between the units, right? So the interaction parameter equals 1/2 here, then you erase, then the entropy and enthalpy match, and it's a random walk, right? So, and then if it gets smaller than 1/2, so you get to higher, chi is 1 over T, so it's smaller than 1/2, then you get expanded coil. But the minute that you go smaller than 1/2 at all, so you get a temperature above the theta temperature, it should immediately be a self-avoiding walk. So it should be a step change in structure, but it isn't. It's kind of a continual change. So Flory and Krigbaum figured out that it could be a continual change if you use this kind of van der Waals kind of approach to talk about the energy contribution to the enthalpic contribution to the energy. So we did this before, right? So we got an equation for R that matched this curve. In fact, the fit there is basically that function for the rate of gyration for the coil size. So anyway, so that doesn't tell you like what's going on inside of it. And what's going on inside of it is basically the opposite of the concentration blob. So as you increase the temperature at a small scale, so as you decrease the temperature at a small scale, it collapses to Gaussian. So with the concentration blob, as you increase the concentration at a large scale, it becomes Gaussian. And with a thermal blob at a small scale, it becomes Gaussian. Because basically the molecular weight dependence of the energetics causes that makes it want to collapse at small scales. It's similar to like why the collapsed coil collapses first at small scale. Like first we get these beads forming, and then the beads form a walk, and finally the whole thing collapses, right? As you go in temperature, dropping the temperature. It's the same thing here. At small scale, you get this Gaussian behavior. You retain the thermal expanded coil behavior at large scale. So it's an opposite transition of the concentration blob. Yeah.
Increase temperature and concentration at the same time,
then you could get both. Yeah, but people don't talk about that. But yeah, you'd get both. So you'd get like collapsed, expanded, collapsed. You get Gaussian, expanded coil, and then Gaussian. But in reality, you need like a decade in size to talk about a scaling regime. And you only have like maybe 1.5 decades total for the polymer chain. So it's pretty hard to see that. Like it'd be hard to demonstrate that that worked. So that hasn't been demonstrated that you can do that. So it's either like thermal or concentration. People don't mix them. As far as I know, I haven't seen anybody mix. And we'll see, you can see even just the paper this week's a tensile, and you'll see that that gets already really complicated because you have the comb polymer, then you have the backbone, which is going through tension because as these kind of balloons stuck to it or expanding, then it's stretching the backbone, right? And also the side chains themselves are expanding, they're being pulled on because they're hitting against each other. So you have, even in that case, you have like, so you have 4 regimes for that in terms of the structure. Like one is where the backbone has flexibility and it can expand to allow the side chains to get bigger, but not hit each other. And finally, that's fully extended. So the initial one is just like everything's free. That's dilute. And then you get to the point where the backbone stretches out. That's regime 2. Then you get, when that ends, when it's fully stretched, then the side chains start to pull up, right? Then it becomes a brush polymer. And then, so anyway, you get 4 regimes. I forget what the 4th one is. So So you get 4 regimes even in that simple system. So it's relatively simple, but so anyway, this whole thing can get kind of like metaphysical, like too much talking about things that you can't exactly measure, really, but on the other hand, like rheologists love this stuff. So they love to do a rheology measurement and say it's because of this thing. And they use some scaling argument. And it's like, yeah, there it is. So it's also a good place to hide whatever you want to. So it's a little bit of but it is like a kind of a coup in terms of understanding things that are complicated, like really complicated systems and talking about how it fits together, So anyway, so let's see. So this is the thermal blob. So this is just a construct of how these things would work. So this is just like equations. This isn't like the physics of it. It's more just like describing it based on the model. So you have the coil size, and it's going to be composed of these thermal or thermic blobs, and they're going to be in a self-avoiding walk at large scale because it's collapsing at the small scale. So that describes the coil size. And then the number of the thermal blobs is going to be the total molecular weight divided by the molecular weight of a thermal blob. So see, it's like all nomenclature for the 3/5 times the blob size. And then the number of thermal blob units, since it's Gaussian, is going to go as the thermal blob size divided by the Kuhn length. So it's like R squared equals NL squared for the blobs, right? So then times the blob size. So that means that the coil size, if you work out all the powers here, ends up proportional to this blob size to the -1/5. Right? So you can see like things can get a little messy. And then you can get them like the weight dependence. It's a good solvent. That means the minute that you get to this away from the theta temperature, higher than the theta temperature, you have a good self-avoiding walk chain. It's just that it's composed of Gaussian chains, Gaussian blobs, right? And then so you can get this size dependence of that based on the blob size, and it's still a good solvent scaling at 3/5. So that means you're in good shape, right? So you can write R. This is just a construct based on the model. Like you have the local Gaussian, the global random self-avoiding walk. But you also have this guy that we had from the Floyd-Krigbaum analysis. We already know what R is, and R here predicts exactly it predicts exactly that curve. So we know that's a fact, right? So we have a fact and we have our fiction. We can equate the two, and the only parameter that's left here, because N, you don't know this guy, you equate the two R's, and you can solve for this guy. And it turns out it's a simple thing. It's just the Kuhn length. So this is a length, so it's got the Kuhn length, and then it's got chi, and that's it. So the larger the chi, the smaller this guy gets, I guess. Right. So it's basically as you make things worse and worse, then the whole thing becomes Gaussian. Right. And as you make things better and better, so then the whole thing becomes expanded coil. Right. So you're kind of eating it up from inside out, and there's a function that just describes that. Right. That can be verified more or less experimentally. So it's been verified. So, right, so that's the idea. That's the thermal blob, which is kind of like the and we already went through the collapsed coil blob. It says blah blah blah. We got all these kind of blobs. So I think the scattering picture is kind of easier to look at a little bit, but maybe not. It depends how you want to look at it. But that's more or less the 3 kinds of blobs here. Yeah. For what? Mhm. Yeah. They're for basically for linear polymers. Yeah. But you'll see like people apply it to other things. I mean, the model originally is linear polymers, but so they're applying it to like grafted polymers on a surface or to polymers attached to a particle. That's where you kind of need these scaling transitions to talk about how big is the thing. actually, like a particle with polymers attached, like the Dowd cotton model, and you want to know how big is that colloidal particle, then you need to, so they're saying there's a concentration gradient in this thing, and that you're going to get this concentration blob is going to change the coil size as you go out, and that's going to impact the total size of it, which is the thing you want to know. So what molecular weight do you need to put on it? And under different solvent conditions, how does the particle size change, you know? So, yeah. Is this pit, what's a mirror? I don't get that. Oh, the bottom and top, yeah, they're just a mirror. I think they just wanted to show, I guess I don't know, it looks like so the grafting point, and then this guy can move over to that one, I guess is what he's showing here. It's probably in the text that describes like why he did it that way. Anyway, it's not really, so you can't really exactly get an appreciation for it because the chains are kind of entangled, right? So it isn't just like one chain isolated, which is the way they're dealing with it. So in actuality, they're like all entangled with each other. So I don't think it's exactly this model is really right, you know, it looks contrived. But basically it's a standard model to talk about a grafted particle and what the actual radius of the grafted particle is. It's popular. This is like a really popular model to talk about for that system. There's no alternative, I don't think, that's been proposed, but so. All right, so yeah, so anyway, this business, so the one thing that was done, so the reason to mention this, I guess, is partly it's in all the books, and also because this paper on this business, this is a concentration blob and the concentration dependence of osmotic pressure, but this was done by this guy Noda, so Sal Noda, who's in Cincinnati. He's kind of affiliated with UC. He's at Procter and Gamble, but he's done stuff with UC quite a bit. So anyway, so this is like 1970s, I think, but 1980s maybe. So this was like one of the first verifications of anyway, these slides aren't different after this. I could go here. All right, so anyway, this is like one of the first verifications of the concentration blob model, and this is the thing you got. So if you go through the Flory description using the Flory-Huggins equation, you can calculate what the osmotic pressure is for the system, right? And you get this equation. So basically, the osmotic pressure at low concentrations is going to give you the molecular weight, and it's going to be the number average molecular weight. So you can get that from the intercept. So these are different molecular weight chains. And from yeah.
So the base osmotic pressure.
Yeah, pi, yeah, this capital pi is osmotic pressure. Yeah, so if you measure that, so you measure that in a membrane osmometer. So you have this kind of setup. I mean, in imagination, it probably looks different, but you have something like a cellulose membrane. The polymers can't go through it. You have solvent on one side and a solution on the other. Right. So, and initially it's a dilute solution because you want the low concentration limit where you get the molecular weight. And then the polymers can't fit through the cellulose membrane, but the solvent can. So that the solvent wants to dilute the polymers, and so you get more pressure on one side, and difference in pressure is the osmotic pressure. That's kind of simple. That's one way to look at it. Like you're trying to dilute it, and the driving force is going to be kind of the tendency to have osmosis, which is going to be driven by the number of particles here. If you look at this, PV is nRT. So it's ideal gas law. So you can look at it that way too, and just say each of these particles is flying around with KT energy. Then you just have the kinetic theory of gases, and that gives you the ideal gas law. I mean, you can Wikipedia that, but basically that's the basis of it, right? So it's the same thing, just saying the particles are free gas atoms, KT energy each. You get that pressure difference. So, but if you start adding more and more particles, and they're polymer chains, and they overlap, then you lose track of the number here. I mean, you lose track of the mass of the particles from this. right? So basically, to get the Flory equation from this thing, what you say is that you say the solvent's chemical potential on this side and the solvent's chemical potential on that side are equal because it's at equilibrium. And also the polymer chemical potential, there isn't any polymer here. So it's basically use a solvent chemical potential, the two, set them equal, and then solve for the pressure thing in this. So the Flory-Huggins equation is actually a Helmholtz free energy, so it doesn't have pressure in it. It's a constant, it's a system with constant volume, so it doesn't have the PV part. So this the Flory-Huggins equation is a Helmholtz equation because it's based on a lattice model and the volume of the system's fixed. So you don't have this PV. So it's a Helmholtz free energy, not a Gibbs free energy, which Gibbs is what you measure in a DSC or something. Like you're in the atmospheric pressure, so the volume can change in the system. You can have thermal expansion, but the pressure is fixed. So that's Gibbs free energy. But if you're doing a molecular simulation on a grid where the volume's fixed, so you don't have thermal expansion, then you get the Helmholtz free energy.
Is it like a short code or something? For the thermodynamics?
Yeah, that's a square thing. So you can say like Helmholtz free energy is A here. Let's see. Let me get rid of this. So A is G. Let's see. A is G PV. Like you go like this is that plus that. Like H is U plus VP. H is also G minus TS. G plus TS. And G is H minus ST. You can use this for 4 different things, but basically that's one of the things you can use it for. But so G is Helmholtz plus PV. So you have to add, if you have the Flory-Huggins equation, you want to talk about pressure, which is what we want to do, then you have to add PV to it to get the Gibbs free energy, which is the definition of the chemical potential anyway. Like the derivative of this with respect to the number of solvent molecules in it is the chemical potential, right? Not the Helmholtz. So you can't exactly get chemical potential directly from the Flory-Huggins equation because it's a fixed lattice without this pressure, without this volume change, like thermal expansion type stuff. Anyway, so this is from Flory's book, like Flory first book, Polymer Chemistry. So this has been around since the 50s. There's nothing new here, but anyway, so I don't really want to go through this exactly, but basically you need to add in this VP thing and you're working with a lattice. Omega is the number of sites in the lattice. And if you're talking about adding one solvent molecule into it, then the lattice actually change the number of molecules in the system, this omega actually changes. You need to do that with respect to NS and the Flory-Huggins equation with respect to the lattice. So you need derivatives of the free energy to get the chemical potential as dg dns. If you want the S chemical potential of the solvent in the 2 phases. The 2 phases would be like with the polymer in it and without on the 2 sides of the membrane. Right. So anyway, so you need to do these derivatives. It gets slightly messy. There's kind of bookkeeping to it. And in the end, you just get this equation from it. So you can work through that if you want. It's kind of messy, like it's tedious, but basically it's here. And it's also in Flory's first book. That's the source of it. And then a lot of people copy from that and then reproduce it, So probably the best place to look at that is in the Flory's first book. But it isn't necessarily fun to do. Anyway, he's got this expression, which doesn't work as you increase the concentration, it doesn't have concentration blob in it, right? So what Noda did was like he figured out that you could put concentration blob into this, use a scaling law and get the actual behavior. So this function, if you get to high concentration, it's going to go with concentration squared, which is like that line. And actual data for this is polystyrene, I think, alpha methylstyrene. So dissolved in toluene. So alpha methylstyrene is something that GE Plastics came up with, and it like mixes with polystyrene, so you can make a blend of the two and make like polystyrene that isn't as brittle by putting it in. Yeah. N's the molecular N. This is the molecular weight of the chain. It's a number average molecular weight. So that's the lowest ordered moment. That's actually the mean molecular weight. And there's like no other way to get it. So you have a distribution and you want to know what's the thing in the center. This gives you the thing in the center. If you lose light scattering, you get the second moment to the first. And then if you use RG, you get the eighth to the sixth. So you get RG is useless. Weight average is pretty good. Number average you kind of need. So this gives you the number average, which is the number, that's the mean. That's the number you usually want. Like what's the mean is kind of what you're thinking of when you say what's the average. Right. So anyway, this is a colligative because it's actually counting like it's counting how many black dots there are. Like it's saying how many, that's what this is N here is counting. Like PV equals NRT, that's counting, it's colligative. So that means you get a number average if it's a distribution. Right. So anyway, it's a nice technique to get that. You can just run it through a GPC too and get all the distributions because you get the whole distribution curve. But anyway, with the correction for the concentration blob, you can get the right scaling out here. So maybe on Monday I'll say that, like how to get that a little bit more into the detail of this, because tomorrow I'm going to do the comb polymer Friday. So anyway, and then since again, like I probably push back a day for the homework because I haven't written it yet. So you don't have a chance to look at it this week. So maybe like Wednesday instead of Monday, I think, because anyway, it's just taking a while to, I don't know what's going on. I've been busy or something, but actually this week I'm less busy than last week. And last week it wasn't any problem. So it's like whatever reason. Oh, anyway, also Friday, so let me just tell you guys before you leave that Friday we have that seminar. So you guys should try to, it's like 4 o'clock, it's a symposium, what did this guy do? There's a symposium, it's gonna be pretty good. There's a poster session. If you can still put in a poster if you want. This guy, Sanat Kumar is gonna give a talk, and then somewhat, it's on MLAI stuff, but basically it's polymer. He's like it'll just be about polymers. I think we've looked at one of his papers this year, and then so it's like an award, and then there's a poster session. It's like 20 posters, so there should be a lot of stuff to kind of, it'll be food and stuff, but it's 4 o'clock until 7, 7 something. So basically, I don't know, come a little bit before 4. There'll be some coffee there at least, and then if you want it, yeah.
Where's the?
It's over in that new building, this Clifton Court Hall. It's over on Clifton. I don't know if you've been in it, but anyway, it's a nice place. It's all brand new, It's got a nice lecture hall. So, and then out in front of it is where the posters will be. And people have them set up before, I think. So if anyone wants to put a poster up, you can do it still. Just email me. I'll put it on this list here. But all right. All right. Hi, you doing?
I think it's a thing of the adapter here.
Oh, yeah. Oh, thank you. Yep. All right.